Tonight, we're going to explore something that most people never think about. You look up at the night sky and you see stars. Thousands of them scattered across the darkness like scattered salt on black velvet. And your brain tells you a story. It tells you that what you're seeing is the universe. All of it, or at least most of it. A vast, beautiful, complete picture of everything that exists. But that story is wrong. Deeply, fundamentally wrong. What you're actually seeing is a tiny bubble. A small, limited region of space that light has had time to reach us from since the universe began. Beyond that bubble is more. Much more. Possibly infinite more. And what exists out there, beyond the reach of any telescope we could ever build, is one of the most unsettling questions in all of science. By the end of tonight, you're going to understand why our observable universe is just a horizon, not a wall. Why something almost certainly exists beyond it. And why the possibilities for what that something might be range from the strange to the truly disturbing. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Let's start with something you can do right now. Go outside on a clear night. Find a dark spot away from city lights. Look up. What you're seeing when you look at that sky is not the present. You're looking into the past. Every single point of light you see left its source years, decades, centuries, or millennia ago. The light from the moon left its surface about 1.3 seconds ago. The light from the sun took about 8 minutes to reach your eyes. The light from the nearest star, Proxima Centauri, left that star 4.24 years before it reached you. When you look at the Andromeda galaxy with your naked eye, a faint smudge in the constellation Andromeda, you are seeing light that left that galaxy 2.5 million years ago. Humanity didn't exist yet when that light began its journey. And when the most powerful telescopes peer at the most distant objects ever observed, galaxies so far away they appear as faint red smears, they're seeing light that traveled for over 13 billion years to reach us. That's the strange thing about the universe. Looking outward in space means looking backward in time. The two are inseparable. Distance and time are the same fabric, stretched and warped together. This is not just a poetic idea. It's a physical reality described by Einstein's theory of special relativity. Space and time are not separate things. They are woven together into a single four-dimensional structure called spacetime. And this single fact that light takes time to travel is what creates the observable universe. It's what creates the horizon beyond which we cannot see. It's what makes the question of what lies beyond so haunting. So what exactly is the observable universe? Let's define it precisely, because the definition matters enormously for understanding why what lies beyond is so strange. The observable universe is not the entire universe. It's the region of the universe from which light has had enough time to reach us since the Big Bang, approximately 13.8 billion years ago. Think of it this way. The Big Bang happened 13.8 billion years ago. Light travels at a fixed speed. So the farthest light we could possibly receive is light that left its source 13.8 billion years ago, right at the beginning. You might think this means the observable universe has a radius of 13.8 billion light years. That would make sense if space were static, if it were just sitting still while light crossed it. But space is not static. Space itself is expanding. It has been expanding since the Big Bang, and it is expanding right now as you read these words, as you breathe, as your heart beats. Because space has been expanding while light traveled through it, the sources of the oldest light we receive are now much farther away than 13.8 billion light years. The universe has stretched out from under that ancient light while it was still in transit. When we do the math, accounting for the expansion of space, the observable universe has a radius of approximately 46.5 billion light years. That means its diameter is about 93 billion light years across. To put that number in any kind of perspective, 1 light year is about 5.88 trillion miles. Multiply that by 93 billion, and the number becomes effectively meaningless to human intuition. It is simply vast beyond any comparison. Within that sphere, this observable universe, there are an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star is a sun, many with their own planets orbiting them. The observable universe contains more stars than there are grains of sand on every beach and desert on Earth. Combined, several times over. And this is just what we can see. Just the bubble. Now here is where things start to get strange. The edge of the observable universe is not a wall. It is not a place where the universe ends. It is simply a horizon. Think about standing on a ship in the middle of the ocean. You can see in every direction up to a certain distance. Then the ocean curves away from you and disappears beyond the horizon. That horizon is not the edge of the ocean. The ocean continues far beyond it. There are more waves, more depths, more creatures, more water, stretching on beyond what your eyes can see. The horizon is a limit of your vision, not a limit of reality. The edge of the observable universe works the same way. It is the cosmic horizon, the point beyond which light has not had time to reach us. But the universe continues beyond it. We know this because there is absolutely nothing special about our location. The universe, as far as we can measure, looks the same in every direction. It has the same density of galaxies, the same distribution of matter, the same temperatures. If our location were near some actual edge of the universe, we would expect to see differences. Fewer galaxies in one direction, a drop-off in matter density, some asymmetry that would hint at a boundary nearby. We see no such thing. The universe looks the same in every direction we observe. This is called the cosmological principle, and it implies strongly that what we see is just a sample of a larger whole. Think about it this way. Imagine you're standing in the middle of a vast, flat plain. You can see for miles in every direction to your personal horizon. Beyond that horizon, you can't see. But the plain continues. Now imagine you're a tiny observer inside that plain, able to see only a bubble of a certain radius around you. You observe the plane to be uniform in all directions. You would logically conclude that beyond your bubble, more plane continues. The same principle applies to the universe. The universe beyond our horizon is not nothing. It is not empty. It is almost certainly more universe. More space, more galaxies, more stars, more matter, more of everything we see around us here. But here is the deeply unsettling part. We can never prove this directly. We can never see beyond our cosmic horizon. Not with any telescope we could ever build. Not with any technology conceivable by physics. The horizon is absolute. It is a fundamental limit, not a technological one. No matter how much we advance, no matter how powerful our instruments become, that horizon remains. The universe beyond it is, in the most literal sense, beyond our reach. Why can't we ever see past it? Let's make sure we understand this because it's important. It's not that our telescopes aren't good enough yet. It's not that we need bigger mirrors or better detectors. It's that light from beyond the horizon hasn't reached us yet. And more than that, due to the expansion of space, light from sufficiently far away will never reach us. Space is expanding faster than that light can travel through it. Think of an ant trying to walk from one end of a rubber band to the other. If the rubber band is stretching faster than the ant can walk, the ant will never reach the other end. No matter how fast the ant walks, the destination keeps receding. Light faces the same problem. At a certain distance, roughly 14 billion light-years from us right now, space is receding from us at exactly the speed of light. Beyond that distance, space recedes faster than light can travel. Light emitted right now from beyond that distance will never reach us. It will travel toward us for billions of years, making forward progress through local space, but the overall distance between us and that light source will grow, not shrink. This boundary is called the cosmological event horizon. It is different from the particle horizon, which marks the edge of the observable universe. These are two separate limits, and both are absolute. The particle horizon marks how far light that was emitted at the Big Bang has traveled. It tells us the current size of the observable universe, 46.5 billion light-years in radius. The event horizon marks how far a light signal emitted right now could ever reach, accounting for acceleration of the expansion. It defines the region of the universe we could ever interact with, even in principle, across all of future time. Both boundaries are real. Both are permanent. Both are consequences of a universe that is not just expanding but accelerating in its expansion, driven by the mysterious force we call dark energy. And both of them mean the same thing for our question tonight. What lies beyond is inaccessible. Not temporarily, not until we develop better technology. Forever, we are sealed inside a cosmic bubble of knowable space, with unknown and perhaps unknowable reality stretching endlessly beyond. So what do we actually know about what lies out there? What does science tell us about the nature of the universe beyond the horizon? This is where the conversation becomes genuinely strange. The honest answer is that we cannot know directly. But we are not completely in the dark. Physics and mathematics give us tools to reason about what the universe beyond the horizon is likely to be like. The first and most straightforward possibility is simply that the universe continues. More space, more galaxies, more matter, all following the same laws of physics we observe here. More of the same, stretching on in every direction. If the universe is infinite, and many cosmologists believe it is, then this continuation is literally endless. There is no center. There is no edge. There is just more universe in every direction without limit forever. This idea that the universe is simply infinite and uniform beyond our horizon is actually the most conservative assumption. It requires no new physics, no exotic structures, no unusual properties. But even this conservative possibility has deeply unsettling implications. Because if the universe is truly infinite, then everything that can happen does happen. Somewhere, infinitely many times. Let that sink in for a moment. An infinite universe contains an infinite amount of matter, arranged into an infinite number of configurations. And a finite number of possible configurations can only account for so much variety. Think about atoms. There are roughly 10 to the power of 80 atoms in the observable universe. That is an enormous number, but it is a finite number. There are a finite number of ways those atoms can be arranged. Now imagine an infinite universe. Infinite regions of space, each containing roughly 10 to the 80 atoms. With a finite number of possible arrangements of those atoms in an infinite space, every arrangement must repeat infinitely. This means that in an infinite universe, there is a region of space, impossibly far beyond our horizon, where the atoms are arranged in exactly the same pattern as in our observable universe. An exact copy. Not just a similar copy. An exact copy. Same galaxies in the same positions. Same stars, same planets, same continents, same cities. Same you lying here reading these words in the same bed in the same room. There is another you infinitely far away, having exactly this experience right now. And another, infinitely many copies of you in infinitely many identical observable universes, scattered through an infinite cosmos. This is not science fiction. This is the direct mathematical implication of an infinite universe with finite possible configurations of matter. It follows from standard cosmology and basic combinatorics. Max Tegmark, a cosmologist at MIT, has calculated how far away the nearest copy of our observable universe would be. The number is so large it can barely be written. It is approximately 10 to the power of 10 to the power of 118 meters away. That number is so incomprehensibly large, it has essentially no meaning to human intuition. It is not 10 to the 118th power. It is 10 raised to the power of 10 raised to the power of 118. A tower of exponents that dwarfs anything in known physics. But in an infinite universe, that distance is not unusual. In an infinite universe, every finite distance is essentially zero. The copies are out there. Infinitely many of them. Right now. But an infinite, uniform universe is just the beginning. Just the first and most conservative of the possibilities. Physics gives us reason to think the reality beyond our horizon could be far stranger than a simple repetition of what we see. Let's talk about cosmic inflation. Because inflation is the key that unlocks some of the most unsettling possibilities for what lies beyond our horizon. Inflation is the theory that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. In roughly 10 to the power of negative 32 seconds, space expanded by a factor of at least 10 to the power of 26. To put that in terms of scale, if you took a proton, a particle far too small to see with any microscope, and inflated it by the same factor, it would become larger than the observable universe is today. That is the scale of inflation. Inflation was not proposed arbitrarily. It was proposed to solve real problems in cosmology. It explains why the universe looks the same in all directions. It explains why the universe is geometrically flat. It explains the pattern of tiny temperature variations in the cosmic microwave background. Every prediction inflation makes has been confirmed by observation. It is one of the best supported theories in modern cosmology, even though the mechanism behind it remains mysterious. But inflation has an implication that its creators did not fully anticipate. An implication that falls directly on our question about what exists beyond the observable universe. That implication is called eternal inflation. Here is how it works. Inflation is driven by a field called the inflaton field. Think of this field as having energy, like a ball sitting on a hillside. The ball wants to roll down to the bottom, but while it is up on the slope, it drives inflation. Eventually, the ball rolls down. Inflation ends. Energy is released. The hot, dense plasma of the early universe forms, and normal Big Bang cosmology takes over. But here is the key. In quantum mechanics, nothing happens uniformly everywhere at the same time. The inflaton field fluctuates. In some regions, it rolls down the hill quickly, ending inflation. In others, it fluctuates back up, continuing to inflate. And because the regions still inflating are expanding exponentially, they grow faster than the regions where inflation ends. The inflating regions always dominate. New regions are always being created faster than old ones stop inflating. This means inflation never fully stops. Globally, across all of space, inflation continues forever. Individual regions stop inflating and become what are called bubble universes. But the space between bubbles keeps inflating, generating new bubbles constantly. This is the eternal inflation scenario. And if it is correct, our observable universe is just one bubble. One tiny region where inflation happened to end, in an eternally inflating background that continues forever. Beyond our horizon, in this picture, there is not just more of our universe. There are other bubbles, other regions where inflation ended, perhaps long ago, perhaps more recently, perhaps right now. And here is where it gets deeply strange. When inflation ends in a bubble, the properties of that bubble depend on how inflation ended and on the state of the quantum fields at that moment. Different bubbles could end up with different properties, different values for the fundamental constants of physics, different masses for the electron or the proton, a different strength for gravity, a different speed of light. In some bubbles, the differences might be small. Physics slightly different from ours, but recognizable. Stars might form, galaxies might assemble, and some form of complexity might emerge. In other bubbles, the differences might be so extreme that atoms cannot form. Stars cannot ignite. Matter as we know it cannot exist. These universes would be cold, uniform, and completely devoid of anything we would recognize as structure. In still others, physics might be so alien that we cannot even imagine what complexity looks like there. Different dimensions, different forces, different rules governing the behavior of whatever passes for matter in that bubble. And if eternal inflation has been running for a long time, and by all indications it has been running since before our universe began and will run forever, then the number of bubbles is not just large. It is infinite. An infinite number of bubble universes, each with potentially different physics, scattered through an eternally inflating multiverse. Each one sealed off from the others by the expanding space between them. Each one completely inaccessible to all the others, including ours. But wait, it gets stranger still. Because eternal inflation is not the only framework that predicts a multiverse. Quantum mechanics independently leads to the same conclusion, from a completely different direction. You are probably familiar with quantum mechanics as the theory of the very small. The theory that describes electrons, photons, atoms, and all of their strange behaviors. Uncertainty, superposition, entanglement. One of the strangest aspects of quantum mechanics is the measurement problem. When a quantum system, like an electron, is not being observed, it exists in a superposition of multiple possible states at once. An electron can be spinning both clockwise and counterclockwise simultaneously. It can be in two places at once. It can have two different energies at once. All of these possibilities exist together, described by the quantum wave function. But when you measure the electron, you always get a single definite result. The electron is either spinning clockwise or counterclockwise. It is in one place or the other. The superposition collapses to a single outcome. This is deeply puzzling. What causes the collapse? What selects one outcome from all the possibilities? This is the measurement problem, and it has bothered physicists since the 1920s. The most widely taught answer is that the act of observation causes the collapse. But this raises its own questions. What counts as an observation? Does a detector count? Does it require a conscious observer? This leads into deeply uncomfortable territory. In 1957, a young physicist named Hugh Everett proposed a radical alternative. What if the wave function never collapses? What if all the possible outcomes of every quantum event actually happen simultaneously in different branches of reality? When you measure the electron and find it spinning clockwise in another branch of the same universe, another version of you measures it and finds it spinning counterclockwise. Both outcomes happen. Reality branches into two. This is the many worlds interpretation of quantum mechanics. And it has profound implications for our question tonight. Because if the wave function never collapses, if every quantum event branches reality into multiple outcomes, then the number of branches is not just large. It is incomprehensibly vast. Every quantum event in the universe creates branches. Every radioactive decay, every photon absorption, every particle interaction. The universe is constantly branching, constantly splitting into parallel versions of itself at every point in space, at every moment in time. The total number of branches is so large it cannot be written or even meaningfully estimated. Each branch is a complete universe in itself, with its own version of every particle, every star, every planet, every person. And crucially, these branches exist. They are real. They are not metaphors or abstractions. In Everett's interpretation, they have the same ontological status as our branch. They are just as real as the universe you experience right now. Many physicists take this interpretation seriously. Not as a speculation or a philosophical fancy, but as the straightforward reading of the quantum mechanical formalism. Some would say it is the most honest reading of the mathematics. But it means that beyond our observable universe, and indeed interleaved with it, is an incomprehensible tangle of parallel realities. All real, all inaccessible to us, all evolving according to the same laws of quantum mechanics. In some of those branches, human history went differently. Wars had different outcomes. Scientific discoveries were made by different people at different times. Random chance created different configurations of matter, different societies, different lives. In others, the differences started earlier. An asteroid that missed Earth in our branch hit it in another. Life never evolved past single cells. Or complex life took a completely different path and produced something we would not recognize as intelligence. In others still, the differences go all the way back to the Big Bang. Different initial conditions, different patterns of quantum fluctuations, producing a universe with different large-scale structure. Different galaxies, different stars, different histories. All of them real. All of them now. All of them forever beyond any possible contact with us. Not because of distance, but because quantum branches do not interfere with each other in any observable way once they have diverged. Let's pause for a moment and feel the weight of what we have described so far. We have established three separate frameworks: an infinite universe, eternal inflation, and the many worlds interpretation, each of which independently implies that reality is vastly larger than the observable universe. And each of them implies not just more space, but more versions of everything. More you, more Earth, more history, more life, more consciousness, an almost incomprehensible proliferation of reality beyond the edge of what we can ever hope to see. This should make you feel something. It might be awe. It might be disorientation. It might be a kind of vertigo, a sense that the ground of reality has shifted beneath your feet. That feeling is appropriate, because what these frameworks are telling us, if they are correct, is that our observable universe is not the world. It is a sample, a tiny, randomly selected sample of a reality so large that the word large does not begin to capture it. Everything you have ever known, every person who has ever lived, every event in all of human history, all of it fits inside a bubble of space that is, in the context of the full multiverse, essentially nothing. A single atom in an infinite ocean. But we have not yet talked about the most mathematically extreme possibility. The one that Max Tegmark calls the mathematical universe hypothesis. The one that, if true, makes everything we have discussed so far look modest by comparison. Tegmark's hypothesis begins with a simple observation. The universe is describable by mathematics. Not approximately, not loosely, but precisely. Every physical process follows mathematical laws with perfect accuracy. Electrons behave according to the equations of quantum electrodynamics. Massive objects curve spacetime exactly as described by Einstein's field equations. Particles interact in exact accordance with the Standard Model. Why? Why should physical reality be mathematical? Why should the universe follow equations at all? This is one of the deepest questions in philosophy of science, and it has troubled thinkers for centuries. Tegmark's answer is radical. The universe is not just described by mathematics. The universe is mathematics. Physical reality is a mathematical structure. There is no difference between the mathematical description and the thing itself. If this sounds abstract, consider what it means. If physical reality is a mathematical structure, then every self-consistent mathematical structure is a physical reality. Every possible set of equations that does not contain internal contradictions describes a real universe. Not hypothetically real, not metaphorically real, actually physically real, in the same way our universe is real. Because in Tegmark's framework, mathematical existence and physical existence are the same thing. This means the landscape of possible realities is not just large. It is the set of all self-consistent mathematical structures. And that set is not just infinite. It is infinite in a way that dwarfs even the infinities we have discussed so far. There are mathematical structures with different numbers of spatial dimensions. 3 dimensions like ours. 4, 5, 10, 26, any number. Each one a potential universe with different physics emerging from the geometry. There are mathematical structures with different fundamental forces. Universes with no gravity or with gravity operating on different scales. Universes where electromagnetism does not exist. Universes where there are 12 fundamental forces instead of 4. There are mathematical structures so alien that they do not contain anything like space or time as we understand it. Universes where the concept of location does not exist. Universes where causality runs in different directions or does not exist at all. And according to Tegmark, every single one of these structures is real. Every self-consistent mathematical universe physically exists. Our universe, the one you are in right now, is just one member of this vast, incomprehensible mathematical multiverse. Why do you find yourself in this particular universe? For the same reason you find yourself in a universe capable of supporting life. Because you are here asking the question. A universe without the right conditions for your existence is not a universe you could ever find yourself in. This is the anthropic principle taken to its mathematical extreme. And it means that the question of why our universe has the particular laws it does, why the constants have the values they have, why physics is the way it is, may have a simple answer. Our universe has these laws because beings like us can only exist in universes with compatible laws. We are not special. We are just the small fraction of all possible mathematical structures that happen to contain conditions suitable for complex, self-aware observers. We have been talking about the universe beyond our horizon in terms of physics and mathematics. But let's bring this back to something more immediate, more personal, more unsettling in a different way. What does it mean for you specifically to exist in a universe with this structure? What does it mean for your sense of identity, your sense of uniqueness, your understanding of what you are? Let's start with the copies. If the universe is infinite, there are exact copies of you. not similar people who made similar choices. Exact copies, atom for atom, quantum state for quantum state, with the same memories, the same personality, the same sense of being a unique individual. Each of those copies is having exactly the experience you are having right now. Reading these same words, thinking these same thoughts, feeling whatever you are feeling as you absorb this information. From the inside, each copy has no way to distinguish themselves from any other. Each one believes with complete justification that they are the original, the unique one. But there is no original. There are infinitely many. What does this do to your sense of self? Your identity is built partly on the feeling of uniqueness, on the sense that your particular history, your particular set of experiences and memories, belongs to you and only you. But in an infinite universe, that feeling of uniqueness is an illusion. Not a comforting white lie, but a fundamental misunderstanding of the structure of reality. You are one of infinitely many identical instances of a particular pattern of matter and information. And it goes further. In an infinite universe, there are not just exact copies of you. There are also near copies. Versions of you where one quantum event, one tiny random fluctuation somewhere in your history, went differently. Maybe in one near copy, a neuron in your brain fired slightly differently 3 years ago, leading to a slightly different decision, leading to a slightly different life. But still recognizably you, still continuous with everything that makes you who you are. And there are farther copies. Versions of you where a major event went differently. Where a relationship ended differently or started differently or never happened. Where a job was or wasn't offered. Where a road was or wasn't taken. And there are distant copies. Versions of you on worlds that differ significantly from Earth. Same biology, same basic human nature, but in a different civilization, a different history, a different context. All of these versions exist. All of them have the same conviction you have right now, that they are the real one. The continuous one. The genuine article. And none of them is wrong. They are all equally real. Now let's talk about something that many physicists find even more disturbing than the copies. Let's talk about what happens to the laws of physics beyond our horizon, in the eternal inflation framework. We established earlier that in eternal inflation, different bubble universes can have different physical laws. Different values for the constants of nature. Different strengths for the fundamental forces. The constants of nature are numbers like the mass of the electron, the strength of the gravitational constant, the charge of the proton, the cosmological constant controlling dark energy. These numbers are measured, not derived. We do not know why they have the values they have. We cannot calculate them from first principles. We simply measure them and put them into our equations. They are the given facts of our universe, unexplained by any deeper theory we currently possess. And they are extraordinarily precisely tuned. Change any of them by even a small amount, and the universe becomes incompatible with life. Sometimes incompatible with any structure at all. If the gravitational constant were slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. Stars would have formed and died too quickly for planets to develop. Life would have had no time to emerge. If the gravitational constant were slightly weaker, matter would not have clumped together at all. There would be no galaxies, no stars, no planets. Just a thin, uniform gas spreading endlessly through expanding space. If the mass of the electron were slightly different, atomic bonds would not work correctly. Chemistry, as we know it, would be impossible. The molecules that make up your body could not exist. If the cosmological constant, the energy density of empty space driving the expansion of the universe, were slightly larger, the expansion would have been so rapid that matter never had time to clump together. No structures would have formed at all. Physicists call this fine-tuning. The constants of nature appear to be adjusted, almost impossibly precisely, to values that allow the universe to develop complexity and life. The precision required is extraordinary. Some see this as evidence of a designer. A conscious intelligence that set the dials of the universe to allow for life. Others find this explanation philosophically unsatisfying. It raises more questions than it answers. The multiverse offers a different explanation. If there are infinitely many bubble universes, each with different values for the constants, then the fine-tuning is not surprising. Most universes have the wrong values for life. But we inevitably find ourselves in one of the rare universes with the right values, because those are the only ones in which we could exist. It is the same logic as asking why you were born in a country with hospitals, rather than a remote wilderness with no medical care. The answer is not that someone designed your birthplace for your benefit. It is that you are more likely to be alive if you were born somewhere with medical care. The anthropic principle again. We observe fine-tuning not because the universe was designed for us, but because only finely tuned universes contain observers to notice the fine-tuning. But this explanation, while mathematically clean, is deeply unsettling in its own way. It means the laws of physics are not necessary truths. They are accidents, lucky outcomes of a cosmic lottery that produced one habitable bubble among an infinite array of uninhabitable ones. The reason the electron has the mass it has is not because physics demands it. It is because in the universes where the electron has a different mass, nobody is there to ask the question. Our laws of physics are the laws of a lucky bubble. Out there, beyond our horizon, are bubble universes where the electron has 1,000,000,000,000 times its mass here. Bubbles where gravity is so strong that nothing can form. Bubbles where the speed of light is different. Bubbles where time flows in a different direction, if time exists there at all. Each of those universes is just as real as ours. Each one is a genuine physical reality, following whatever laws govern it. But in most of them, there is no one to know that they exist. The self-awareness of the universe is concentrated in the rare bubbles that happen to be compatible with it. There is another possibility we have not yet discussed. One that is perhaps the strangest of all. One that does not come from cosmology or quantum mechanics, but from a peculiar feature of how our own universe is structured. Consider the cosmic microwave background. The faint glow of radiation left over from the Big Bang, permeating all of space at a temperature of about 2.7 Kelvin. It is the oldest light in the universe. The afterglow of the hot, dense state everything began in. When we map the cosmic microwave background in detail, we find tiny temperature variations. Hot spots and cold spots, varying by about 1 part in 100,000. These variations are the seeds of all structure in the universe. The hot spots and cold spots in the CMB originated as quantum fluctuations in the very early universe, stretched to cosmic scales by inflation. They represent the pattern of density variations that, over billions of years, collapsed under gravity to form galaxies, clusters in the cosmic web. Now, in 2015, researchers analyzing CMB data noticed something strange. There appear to be subtle anomalies in the CMB pattern that do not match what standard cosmology predicts. Unexpected alignments, unusual cold spots, asymmetries that in the standard model should not be there. One of the most discussed anomalies is the cold spot, a region in the southern sky where the CMB is significantly colder than the surrounding area. Not dramatically colder, but cold enough to be statistically unusual. One explanation for the cold spot is the presence of a supervoid, a region of space nearly empty of galaxies, causing light traveling through it to lose energy and arrive at us slightly cooler. And indeed, there does appear to be a large void in that direction. But another explanation, one that some cosmologists have taken seriously, is that the cold spot is evidence of a collision between our bubble universe and another bubble universe in the eternal inflation multiverse. If our bubble universe and another bubble universe were once close enough to touch, the collision would have sent a shockwave through our universe. That shockwave would have left an imprint on the cosmic microwave background, a distinctive circular pattern of temperature variations. The cold spot in this interpretation is a bruise on the cosmic microwave background, the scar left by an ancient collision between universes. Evidence that we are not alone in the multiverse, that other bubbles exist and that they can, in rare circumstances, brush against ours. This interpretation is controversial. Most cosmologists think the cold spot has a more mundane explanation. The statistics are not yet compelling enough to claim a bubble collision as the cause. But the possibility is real. The physics allows for it. Bubble collisions can happen in the eternal inflation scenario. And if they do happen, they leave exactly the kind of imprint we might be seeing. We may already have evidence of other universes in our data. Let's talk about the shape of the universe. Because the shape of our universe has direct implications for what lies beyond our horizon, and the current evidence is deeply interesting. One of the most fundamental questions in cosmology is whether the universe is finite or infinite. Whether space eventually wraps back on itself like the surface of a sphere, or whether it extends without limit. General relativity describes the geometry of spacetime, and it allows for multiple possibilities. The universe could be positively curved, like the surface of a sphere. Travel far enough in one direction, and you would eventually come back to where you started. The universe could be negatively curved, like a saddle shape. In a negatively curved universe, parallel lines diverge from each other. The geometry is everywhere locally different from flat space. Or the universe could be flat. In a flat universe, the rules of Euclidean geometry hold on large scales. Parallel lines stay parallel. The angles of a large triangle add up to exactly 180 degrees. Our measurements of the cosmic microwave background, particularly from the Planck satellite, tell us that the universe is flat to extraordinarily high precision. Within the limits of our measurements, the curvature is exactly zero. A flat universe can still be finite. It could be structured like a torus, a donut shape, where space wraps around in all directions. Travel far enough and you come back to your starting point, even though the local geometry is flat. In a finite flat universe, you would eventually see the same galaxies appearing in multiple directions. Your observable sphere would eventually overlap with itself. You might even see the Milky Way in the distance, recognizing it as our own galaxy seen from far away. We have looked for this pattern. It would appear as circles of matching temperature in the cosmic microwave background, regions where our past light cone has intersected itself. We have not found such circles, which rules out the smallest finite topologies. But it does not rule out finite universes much larger than our observable sphere. If the universe wraps around, but the wraparound distance is much larger than 93 billion light-years, we would never be able to see it. The pattern would be there, but too spread out for us to detect. The current data favors a universe that is either infinite or so large that its size is completely undetectable. Either way, the conclusion for our question is the same. What lies beyond our horizon is vast and unobservable. Let's think now about something that rarely comes up in these discussions. The emotional and philosophical weight of living in a universe structured this way. Because it matters, it changes things. For most of human history, people believed the universe was human-sized. The stars were lights in the celestial sphere not so far away. The Earth was the center. The cosmos was built for us, or at least arranged around us. Then Copernicus showed us that the Earth orbits the Sun, not the other way around. The first step in a long process of decentering, of discovering that we are not where we thought we were. Then we discovered that the Sun is just one star among hundreds of billions in the Milky Way. Then we discovered that the Milky Way is just one galaxy among trillions in the observable universe. Each discovery pushed us further from the center. And now we face the next step. The observable universe itself, all 2 trillion galaxies of it, is just a bubble in something vastly larger. We are not at the center of the observable universe, which is itself not the center of anything. We are arbitrarily located in an arbitrarily selected bubble. Every instinct we have says we are important. Evolution built us to feel central, to feel like the main characters in the story. But the universe, at every scale we examine, tells us we are not central. We are peripheral. We are local. We are a tiny exception in a vast, mostly empty, mostly unconscious reality. This is the Copernican principle taken to its ultimate conclusion. Not just that Earth is not the center. Not just that the Sun is not the center. Not just that the Milky Way is not the center. But that our entire observable universe is not the center. There may be no center. In an infinite multiverse, the concept of center has no meaning. And yet here we are, reading, thinking, wondering, feeling the weight of these ideas pressing against the limits of our intuition. Experiencing the disorientation of confronting a reality that does not care about our comfort. The fact that we can even ask these questions is remarkable. Most of the matter in the universe, most of the stuff that exists cannot wonder. Hydrogen gas does not contemplate its place in the cosmos. Neutron stars do not ask what lies beyond the horizon. We do. This strange, temporary, fragile arrangement of atoms that is a human being is capable of reaching beyond its own existence, beyond its own small slice of spacetime, and grasping at the structure of the whole. And we are doing it right now, lying in the dark, letting these ideas wash over us, feeling the size of something that cannot be held. That capacity, that reach, is not nothing. It might be the most remarkable thing in the observable universe. Possibly in the multiverse. Let's address the obvious question. If we can never see beyond the observable horizon, if the multiverse is in principle undetectable, does any of this matter? Is it science or is it metaphysics? This is a real debate among physicists and philosophers of science. Some argue that a theory that makes no testable predictions is not a scientific theory at all. It is speculation dressed in mathematical clothing. Karl Popper, the philosopher of science, argued that a theory is scientific only if it is falsifiable. Only if there is some possible observation that could, in principle, show the theory to be wrong. Every instinct we have says we are important. Evolution built us to feel central, to feel like the main characters in the story. But the universe, at every scale we examine, tells us we are not central. We are peripheral. We are local. We are a tiny exception in a vast, mostly empty, mostly unconscious reality. This is the Copernican principle taken to its ultimate conclusion. Not just that Earth is not the center. Not just that the Sun is not the center. Not just that the Milky Way is not the center. But that our entire observable universe is not the center. There may be no center. In an infinite multiverse, the concept of center has no meaning. And yet here we are, reading, thinking, wondering, feeling the weight of these ideas pressing against the limits of our intuition, experiencing the disorientation of confronting a reality that does not care about our comfort. The fact that we can even ask these questions is remarkable. Most of the matter in the universe, most of the stuff that exists cannot wonder. Hydrogen gas does not contemplate its place in the cosmos. Neutron stars do not ask what lies beyond the horizon. We do. This strange, temporary, fragile arrangement of atoms that is a human being is capable of reaching beyond its own existence, beyond its own small slice of spacetime, and grasping at the structure of the whole. And we are doing it right now, lying in the dark, letting these ideas wash over us, feeling the size of something that cannot be held. That capacity, that reach, is not nothing. It might be the most remarkable thing in the observable universe. Possibly in the multiverse. Let's address the obvious question. If we can never see beyond the observable horizon, if the multiverse is in principle undetectable, does any of this matter? Is it science or is it metaphysics? This is a real debate among physicists and philosophers of science. Some argue that a theory that makes no testable predictions is not a scientific theory at all. It is speculation dressed in mathematical clothing. Karl Popper, the philosopher of science, argued that a theory is scientific only if it is falsifiable. Only if there is some possible observation that could, in principle, show the theory to be wrong. What if beyond the observable universe, the very concept of beyond breaks down? What if the universe does not simply continue beyond our horizon, but something stranger happens to the structure of space and time out there? Some models of quantum gravity, the attempt to unify general relativity with quantum mechanics, suggest that spacetime itself is not fundamental. That space and time are emergent properties, arising from something deeper. In these models, spacetime is like temperature. Temperature is real and measurable, but it is not a fundamental thing. It emerges from the collective behavior of vast numbers of atoms. You cannot have a temperature unless you have matter to give it meaning. Similarly, spacetime might emerge from something more fundamental. Some underlying quantum structure from which space and time crystallize under the right conditions. Something that has no direct analog in our experience of the world. If spacetime is emergent, then beyond the observable universe, the conditions might not be right for spacetime to emerge. Beyond the cosmic horizon, the underlying quantum substrate might exist in a state where the concept of space has no meaning. There might be no beyond in any geometric sense. Not empty space extending to infinity. Not other bubble universes separated by distance. But something that our mathematical tools can gesture at but cannot fully describe. This is the frontier of physics. The place where the equations start to break down, where the models begin to fail, where honest scientists say they do not know. What lies beyond the horizon might require a theory of quantum gravity to properly describe, and we do not yet have that theory. We have candidates. String theory proposes that the fundamental entities are not point particles but one-dimensional strings, vibrating in 10 or 11 dimensions, with 6 or 7 of those dimensions curled up at scales far too small to observe. String theory predicts an enormous number of possible vacuum states, perhaps 10 to the power of 500, each corresponding to a different universe with different physics. Loop quantum gravity proposes that spacetime itself is quantized, made of discrete units at the Planck scale. That there is a smallest possible length, below which the concept of distance loses meaning. Causal dynamical triangulations, entropic gravity, emergent spacetime from quantum entanglement. Each of these approaches suggests that the bedrock of reality, the structure of space and time itself, is not what it appears to be at the scales we can observe. And if the foundation is stranger than we thought, what lies beyond the horizon might be stranger still. Not just more of the same, not just other bubbles, but something for which we do not yet have words. We are approaching the end of tonight's journey. And I want to bring it back to something small. Something immediate. Something that fits in your hands. You exist. Right now, in this moment, you exist. You are a particular arrangement of atoms, a particular configuration of matter and energy that has achieved the remarkable trick of being aware of itself. Your existence is not guaranteed. It is not necessary. Of all the configurations that matter could have taken in this observable universe, only a tiny fraction could give rise to beings like you. And of those, only a tiny fraction would ever ask the questions you are asking tonight. The atoms in your body were forged in the cores of stars, scattered into space in supernova explosions, gathered by gravity into clouds that became new solar systems, assembled by chemistry and biology over 4 billion years into the form that is you. And here you are, made of stardust, lying in the dark, contemplating the edge of everything, reaching with your mind toward a horizon that no physical thing could ever cross, feeling the weight of an infinite reality that you can conceive of but never fully grasp. That reach is not futile. The fact that you cannot verify the multiverse does not make the question meaningless. The question itself, the act of asking it, of following physics to its logical conclusions, and sitting with the discomfort of not knowing the answer, is part of what makes human consciousness remarkable. We are the universe knowing itself. In us, the cosmos has developed a way to ask about its own nature. And it turns out that when it asks, the answers are more unsettling than it expected. The universe is stranger than we needed it to be, bigger than we needed it to be, more various and more alien than any civilization has imagined. And we know this. We, these temporary arrangements of matter on a small planet orbiting an ordinary star in one of 2 trillion galaxies, in a bubble of space, floating in something far larger and stranger than we can see. We know this, and we continue. We continue asking. We continue reaching. We continue looking at the night sky and feeling the pull of what lies beyond the edge of what we can see. So what does exist beyond the observable universe? The honest answer is that we do not know. We may never know. The horizon is real and it is permanent. But physics gives us reasons to believe that something does exist beyond it. Not nothing, not emptiness, but reality in some form. It might be more of the same. An infinite continuation of the universe we inhabit, with more galaxies, more stars, more planets, and more versions of you having this exact experience right now. It might be other bubble universes sealed off from ours by expanding space, each with its own laws of physics, its own history, its own forms of complexity or their absence. It might be the branching structure of quantum mechanics, an incomprehensible tangle of parallel realities, all real, all diverging from each other with every quantum event. It might be an infinite landscape of mathematical structures, each one physically real, each one a universe unto itself, the full space of possible existence rather than just our corner of it. Or it might be something we have not yet imagined. Something that requires physics we have not yet discovered. Something that would require a new framework entirely to describe. We do not know, and that not knowing is not a failure. It is the current edge of human knowledge, and it is remarkable that we have gotten this far. That we can map the observable universe to the precision we can. That we can follow the implications of our theories to the conclusions we have explored tonight. The boundary of the observable universe is not a wall we have crashed into. It is a horizon we are still learning to interpret. Every improvement in our telescopes, every refinement of our theories, every careful analysis of the cosmic microwave background brings us fractionally closer to understanding what that horizon means. And in the meantime, we live here, in this bubble, with these stars and these galaxies and these questions, with the permanent mystery of what lies beyond as a companion to everything we do. The universe is vast beyond comprehension. The multiverse, if it exists, is vaster still. And we are here, small and temporary, and somehow capable of grasping at both. That is not terrifying. Or rather, it is terrifying and beautiful in equal measure. The terror and the beauty are the same feeling, looked at from different angles. Tonight, wherever you are, whatever you are doing, you are at the center of your own observable universe. A bubble of spacetime 46.5 billion light-years in radius, containing 2 trillion galaxies, billions of years of history, and an unfathomable wealth of experience and complexity. And beyond that bubble, something continues. Something real, something vast, something we may never understand. It stretches on in every direction, past every horizon, through every possible branch of every possible quantum event, into a space so large the word infinite barely begins to describe it. And somewhere out there, impossibly far beyond any horizon, there may be another you, lying in the dark, reading these same words, feeling the same vertigo, looking up at the same infinite ceiling of the unknown. They are wondering what lies beyond their horizon, just as you are wondering what lies beyond yours. And the answer, for both of you, for all of the infinite versions of you scattered through the incomprehensible vastness of whatever the universe truly is, remains the same. We do not know yet, but we are still asking. And that, in a universe this large and this silent, might be the most remarkable thing of all. Sleep well tonight, knowing that the universe is larger than your fear of it, older than your questions about it, and stranger than any answer it has given us so far. The darkness outside your window reaches all the way to the edge of everything. And beyond. Let's spend a moment with the darkness itself, because most people look at the night sky and experience it as an absence. As simply the space between the stars. As nothing in particular. But the darkness between stars is not empty. It is not nothing. It is filled with things that are invisible to our eyes, but real and physically significant in ways that shape everything we observe. The darkness between stars in our galaxy is filled with gas and dust, the raw material for new stars and planets. Clouds of hydrogen and helium and heavier elements drifting slowly in the dark. The darkness between galaxies is filled with an extremely thin but non-zero plasma of ionized gas, heated by the radiation of billions of galaxies, and stretching through the intergalactic medium everywhere. The darkness between galaxy clusters is threaded with the invisible scaffolding of dark matter, the gravitational skeleton of the cosmic web on which all visible structure is built and organized. And pervading all of space, in every direction at every location, is the cosmic microwave background. The ancient light from the Big Bang, now cooled to just 2.7 degrees above absolute zero. That CMB radiation is hitting you right now. Photons from the very edge of the observable universe, from the earliest moment light could travel freely, are reaching your body constantly and continuously. Every second, hundreds of these ancient CMB photons pass through your hands, through your eyes, through your entire body. Light nearly 14 billion years old, traveling from the edge of everything to reach you. You are not separate from the observable universe. You are inside it, bathed in the oldest light that exists, threaded with cosmic rays from distant supernova, immersed in fields from every direction simultaneously. The darkness you see when you look at the night sky is not an absence of reality. It is reality in forms your eyes are not designed to detect. The universe is denser and stranger than it appears. And beyond the edge of that universe, in the regions we cannot see and cannot reach, the same density and strangeness continues. More fields, more radiation, more structure, more history, more of everything. The nothing beyond the horizon is not nothing. The darkness beyond the furthest galaxy is not a void. Reality does not become thin or sparse or absent as it recedes beyond our ability to observe it. It continues to be dense with physics, with structure, with events, with history, with consequences. The universe does not care about our ability to observe it. It simply continues regardless of our horizons. That continuation is what tonight has been about. Not the mechanics of why we cannot see it, important as those mechanics are. But the fact that what we cannot see is real and is out there and is vast. The darkness outside your window is not the end of anything. It is the beginning of everything you cannot see. It reaches to the horizon and beyond the horizon, and beyond every horizon that exists in any direction. Somewhere in that darkness, 46.5 billion light-years from where you are lying right now, ancient photons from the Big Bang are hitting matter that has never been observed by any eye or any instrument. Somewhere farther than that, beyond the horizon, are galaxies that have existed for billions of years without ever being known. Stars that have lived and died in complete observational privacy. Worlds that have orbited their suns through billions of sunrises, without a single observer anywhere in the universe having any knowledge of their existence or their motion or their beauty. And perhaps in some of those unobserved regions, minds have formed. Briefly, temporarily, looking up at their own night sky, seeing their own version of the darkness, wondering about their own horizon. Wondering if something exists beyond what they can see. Asking the same question you are asking tonight. Getting the same honest answer. We do not know. But something is out there. Something real. That shared uncertainty, stretching across billions of light years between minds that will never know each other exist, is one of the strangest and most quietly moving aspects of the universe we inhabit together. So what exists beyond the observable universe? After everything we have explored together tonight, after 5 strange and unsettling possibilities, the honest answer remains that we do not know. We may never know. The horizon is permanent. The physics that creates it is the same physics that governs everything we have ever observed. It will not yield to any instrument or patience. But physics gives us strong reasons to believe that something does exist beyond it. Not nothing, not emptiness, but reality in some form, vast and strange and continuing beyond any possible horizon anywhere. It might be more of the same. An infinite continuation of the universe we inhabit, with infinite copies of everything we know repeating through a cosmos so large the word infinite barely fits. It might be other bubble universes, each with potentially different physical laws, sealed off from ours by expanding space, each one a complete reality with its own history and its own nature. It might be the branching structure of quantum mechanics, an incomprehensible tangle of parallel realities, all equally real, all diverging at every quantum event across all of time and space. It might be an infinite collection of mathematical structures, each one physically real, the full space of possible existence rather than just this one corner of it that we happen to inhabit tonight. Or it might be something we have not yet imagined, something requiring physics we have not discovered, concepts we have not yet formed, language we have not yet needed or developed or invented. We do not know. And that not knowing is not a failure. It is the honest and current edge of human knowledge. Frontiers, by definition, always lie at the edge of what is presently known. Every improvement in our telescopes, every refinement of our theories, every careful new analysis of the CMB moves us fractionally closer to understanding what the horizon actually means for us. We do not get past it, but we come to know it better. We understand what it implies. We learn the shape of the reality we are sealed inside of. We approach the mystery more carefully each year. And in the meantime, we live here, in this bubble, with these stars and these galaxies, and these questions we cannot fully answer and cannot bring ourselves to stop asking in the dark. Tonight, wherever you are at the center of your own observable universe. A sphere of spacetime containing everything you have ever known or seen or measured or understood. And beyond that sphere, something continues. Something real and vast and strange. stretching in every direction through every possible branch, past every horizon into a space beyond any description we have. Somewhere out there, impossibly far beyond any horizon any of us will ever see, there may be another version of you. Lying in the dark, reading these same words, feeling this same quiet vertigo,